All right, welcome back, grade 11. Today we're working on the last two topics in the topic of energy. And those two topics are power and efficiency. So good deal for you. You get a 2-for-1 this week. I'm sure you're all very excited. So the first thing we're going to talk about is something called power. Now, energy flows from one object to another. So, for example, if I am pushing a ball upwards, the chemical energy that was stored in my muscles, that was a chemical potential energy, is being converted into kinetic energy by getting my muscles to actually move. And then once my muscles are moving, they're going to lift up that object, say it's a ball that I'm throwing up in the air. And so the chemical energy turned into kinetic energy in my muscles, and that kinetic energy transferred into kinetic energy and potential energy in the ball. So it went from my muscles into the ball. So it's going from one place to another. And how quickly energy is transferring, how quickly energy is going from one place to another or from one form to another even, is what we refer to as power. Now, whenever you see this word here, rate, whenever you see rate in a physics context, we're really always saying how much something is transferring per second. So if you think of velocity, velocity could be described as the rate at which a position is changed. So we would have our distance divided by time. And so like any kind of rate that we can think of, acceleration is the rate of change, how quickly the velocity is changing for a given time. So my velocity is how quickly distance is changing per time. Acceleration is how quickly velocity is changing per time. And likewise, energy or power is also how quickly energy is flowing divided by time. Now there is another formula, we're not really going to focus on it here, but it might come in handy. It's kind of just a shortcut. You can say that power is the force times velocity. Okay, and if you want to show that for yourself, we know that energy is equal to force times distance. So really what this is saying on the left-hand equation here is force times distance divided by time, because it's energy divided by time. But we can also write that as force times distance divided by time, or force times velocity. Now, you may say, what is the energy of power? And my response would be, yes, that's correct. See, this is a physics joke that every single physics teacher has to say because what is the unit of power? That's correct. The watt is the unit of power. So it's a capital W for the watt, named after James Watt, and it is the unit that we use for discussing power. And I'm sorry, I just can't help myself. You have to throw a physics pun in there. So how much power does a 60, and this question is actually incorrectly worded. This should say, how much energy does a 60-watt light bulb use in 1 month? So if you leave a 60-watt light bulb on for an entire month, how much energy would you be consuming? And so I'd like you to pause the video and try answering this question here. So we've got the equation just to the left of us here, and we can answer it quite easily. Just remember that you'll have to convert month into our standard unit of seconds, obviously. Okay, so pause the video here and give it a try. All right, well, now that you're back from completing the problem yourself and you found the answer, let's go over it as a class just to make sure. So our original equation is the power is just our energy divided by time. So if we rearrange this equation, we multiply both sides by time, and we're going to get energy equals power times time. Now in this case here, the power is 60 watts, but the time is a bit unclear. Now there's two options for solving this, and I'd like you, especially because it's going to help you with our bonus question at the end, I'd like you to try doing it this way. So the first way you're probably going to use is going to go 1 month. Okay, well, we'll call that 30 days. And then we're going to do the conversion here. So the 30 days is going to be, well, we know in 1 day there's 24 hours, and in 1 hour there's going to be 60 minutes, and in 1 minute there's going to be 60 seconds. So that's how we would calculate that. we're going to take it and go 30 times 24 times 60 times 60. And that's going to give us 292, let's see, 259, 2000. So we'll just call this 2.6 million. Let's do that. 2.6 times 10 to the 6 seconds. So that's how many seconds are in a month. Now the other way that you can solve this is just directly. So what I'm going to say here is energy is power times time. This is going to be 60 joules per second. But now we want to go to find out the amount of time. So I'm going to say we're going to multiply this by 1 month, and then we're going to do all of this conversion all over again. So yeah, I guess I should have mentioned here, 1 watt is equal to 1 joule per second. Same thing, it's just 1 joule in 1 second is 1 watt. That's how we define that unit there. Okay, so times 1 month. And then again, we're going to do the exact same thing. So we're going to say times 30 days per 1 month times 24 hours per day times, I'm just going to do a shortcut here, times 3,600 seconds per hour. And we're going to get our answer here. You'll notice that at the end, in terms of the units that have canceled, my months canceled there, my days canceled there, my hours canceled there, and look, I got a second on the bottom and a second on the top. So if you look at the units, all that's left over is the joules. And so that's going to tell me my answer here, and I know that I've done it correctly in terms of the cancellation because I'm left with joules. So both of these ways are fine. This is just kind of the second method here. It's sort of the next level way of solving these, just doing these conversions as part of your calculation. So what we had before was this number of seconds, and we're going to multiply it by, we're going to multiply this answer and by 60 joules. So that's going to give us our answer here, 1.6 times 10 to the 368. 1.6 times 10, or 1.56 times 10 to the 8. And that's going to be in joules. So how much energy? That's the amount of energy that was used there. Okay, so we're used to using watts and joules, or we're used to using watts now. One of the units that your parents are probably more familiar with, if you're asking how much energy you've used because you keep leaving the lights on when you leave the room behind you, and your parents are annoyed because they're the ones paying the electricity bill, not you. Well, when they're looking at the electricity bill, guess what they're looking at in terms of units? They're looking at something called the kilowatt hour. So this is a common unit that you would see in the adult world when you have to finally pay your own electricity bill. So when energy is used, you'll notice that it's energy, but it's measured in something that has watts, but also that has time. So hopefully this makes sense. If we look at this equation here, energy is power times time, well, we're measuring energy in something that has units of power, kilowatts, and time in hours. So pause the video and try and tell me how many joules, or try and find for yourself, how many joules are there in 1 kilowatt hour? Because if your power bills had something in joules, it would just be a massive number, and so to kind of reduce that, we use the kilowatt hour. So try and pause the video to calculate what that unit is going to be. Okay, if you're back from this, we're going to try and solve this together. So energy is power times time. In this case here, energy is, or the power is a kilowatt. So 1 kilowatt is going to be 1,000 watts, and we're measuring it by an hour. So I could multiply, I could do this 2 ways here, 1 hour, and then I'm going to say how many, in 1 hour there's going to be 3,600 seconds. Yeah, we'll just do it that way. We've already got our answer there. So now we have watt seconds. And you can see here that a watt multiplied by a second is the same as a joule. So remember, 1 joule per second equals 1 watt. And so you could say that 1 watt times 1 second equals 1 joule. So if a watt means that I'm using 1 joule of energy every single second, then if I use 1 watt for 1 second, I've transferred 1 joule. Hopefully that kind of makes sense there. And this is going to be our answer here. So if energy is measured in kilowatt hours, then 1,000 watts, 1 kilowatt, times 1 hour, which is 3,600 seconds. That's going to give me 3.6 times 10 to the 6 joules, or we can just say 3.6 megajoules, because mega is times 10 to the power of 6. So 1 kilowatt hour is equal to 3.6 megajoules. So there you go. Learn something new, so that way when you pay your bills in the future for electricity, you'll know exactly how much energy you consume for the month. So that is essentially all there is for power. There's not a huge amount of information. It's simply how quickly energy is going from one place to another. So now what about efficiency? Well, with efficiency, there's going to be two formulas that you can use. So first of all, I'm going to show you this symbol. The unit of efficiency, well, I'll ask you to try and figure that out for yourself. So first of all, what is this symbol? The symbol is this letter here. This is the Greek letter eta. Let's try and draw that again a bit better. Essentially, it looks like a sort of a fancy script N, but the second end of it goes way down. So this is eta. This is our symbol for efficiency, and the formula for that is, well, there's two of them that we can use. So eta can either be the energy out, and sometimes called the useful energy out, and that's divided by the total energy that you put into the system. So, for example, something with 50% efficiency means that out of every, say, 100 joules that I put into it, 50 joules comes out as useful energy of some sort. So we don't count the energy that is wasted. Now, typically when energy is wasted, the form of energy it's going to take is going to be heat. It could also be sound energy. Sound would be wasted energy. For example, if you've got a motor and your motor is making a bunch of extra noises, that's a sign that there's some sort of wasted energy there. So if you're hearing a lot of screeching or something coming out of your engine, it probably means the parts are rubbing together, creating friction, and wasting a bunch of energy. So it's useful energy out divided by total energy in. So we just usually write it as E out over E in, but we really should be thinking of it in terms of the useful energy that's coming out divided by the total energy that's going into the system here. Now, you have the option, and so it just depends on what you prefer. You can multiply this by 100%. So when you're writing efficiency, you can say 50%, but you can also just say 0.5. They would mean the same thing. Now, as I said before, there is one other formula that we can use, and it's the same thing, but instead of using energy, we're now using power. So it could be useful power out divided by total power in. And this should make sense, because remember that power equals energy times time. So in this case here, power out over power in is going to be energy out times time divided by energy in times time, and which is still correct, as it's the same as the first formula here. If we were to cancel out the t's, we're going to end up getting energy out over energy in, which is exactly what we had on the left side over here. So both of those are correct formulas to use. It's just a question of what information do you have. If you're given the power out and the power in, we'll use that in your formula. If you're given the energy out and the energy in, well, then use that in the formula. It just depends on what serves your purposes. So let's try a problem here. So this is a little bit tricky. You've got to kind of solve this in two parts. And I'd like you to pause the video and give this a try for yourself. Okay, so pause the video now. Okay, so if you are just coming back, let's solve this problem here in two parts. So part one, I'm going to look at the incandescent bulb. So incandescent bulbs are the ones that you see with like the filament in them, the really hot piece of wire and of the bulbs from 10, 15 years ago that everyone would have had in their kitchen before they all switched to LED lights or halogen lights. Okay, so you've got an incandescent bulb, and the efficiency is around 5%. So that is true, they are very, very inefficient. Now, a CFL bulb uses around 13 watts to get the same output as a 60-watt incandescent bulb with 5% efficiency. So what is the CFL's efficiency? And this is the compact fluorescent light. So these ones are the ones that are, you might see a light bulb in the store that looks like kind of like a weird helix-y shape that all wraps around each other. I don't know, the weird bulbs that you see that they don't look like this. So this is incandescent on the right, this is a CFL on the left. I should probably get a better picture to show you. Okay, I'll put a picture up on their notes here. Okay, so this is an incandescent bulb, and we're getting the power output with 5% efficiency. So here's what we know. We know for incandescent, if we're writing down our information, we know that our efficiency equals 5%. I'm just going to write that as 0.05. Both are correct to say. I know that the output is a 60-watt bulb. Now the wattage here refers to how much energy is being used. So they tell you 60 watts because they're trying to help you estimate what your power bill might be, for example. So that means that that energy, the light bulb itself, is using 60 watts. So would that be the output or the input? Well, the answer is that that would be the power input. So you're taking from the wall, for example, you plug that lamp into the wall, you're taking 60 watts of power through that power socket. So that's going to be 60 watts. And so there's only one bit of information we're missing, and that is the power out of the incandescent bulb. Now, if we go over to the CFL, then we have this information. We know that our eta, our efficiency, is going to be, oh, that's what we're trying to find out. We also know that our power out, well, it says here they get the same output power as the 60-watt bulb. So what we know for power out is going to be the same as this power out. So they're getting the same output. And then also it says here it's 13 watts, so that's going to be our power input. They're only taking less than a quarter of the amount of energy that the incandescent bulb is going to use. So in order to solve the eta of the CFL, we would need to find, or the efficiency of the CFL, we would need to find the power out first. So let's try that one first. So here's our formula. Eta, or efficiency, equals power out over power in. So power out, if we rearrange for this, is going to be our eta times our power in. And in this case, this is going to be 0.05 times 60 watts. By the way, I forgot to ask or answer this question earlier. So what are the units for efficiency? So give yourself a second, pause the video if you need to. You may see this right away, you may not. But if you don't see it right away, try pausing the video for just another moment to see if you can solve this. If you are back, or if you have already seen it, hopefully you'll see that it is going to be a unitless quantity. So for example, if we look at this over here, it's going to be joules per joule. Well, if I take a joule and divide it by a joule, I don't have a unit left. Here it's going to be watts per watt. Again, it's going to cancel out. So efficiency is unitless. Okay, so if we're going back, a reason why I asked is just because this is blank here. So in this case here, we have efficiency of 5%, or 0.05. We're going to multiply that by 60. That means that the output power, all that we're getting from the lamp, is 3 watts. So you're giving it 60 watts, and all you're getting out is 3 watts worth of light energy. And in this case, the light energy is the useful energy. That's what we want a light bulb for, is to create light, and so that's going to be the part that's useful. So what that's also telling us, just as a side note, is 57 watts is wasted. And that's going to be as heat, primarily. So those bulbs get hot, 57 watts of that is going towards heating up the air around the light bulb, not very particularly useful, and 3 watts is going to actually brightening up your house. Okay, so now we've got a little bit of information here, which is that it's still going to put out 3 watts. It has the same output, so 3 watts is the output. The input's 13 watts, and so what's the efficiency? Well, this should be straightforward to solve. It's going to be power out divided by power in, and 3 divided by 13 gives us 23%. So this is going to equal, either you can say 0.23 or you can say 23%. So about almost 5 times, so 4.6 times the amount of efficiency, or 4.6 the efficiency of a CFL. And so that's, or sorry, of an incandescent bulb. So that's why hopefully your house is also converting towards CFL bulbs as opposed to those old school incandescent bulbs. Okay, now this last question here, this one I'm putting as the bonus question for the week. So if you want to give this a try, I would strongly encourage you to do this. If you can try this one, then you have a really good grasp of power and efficiency. If you're finding this difficult, I have put a number of hints just in terms of what order you should try and solve this. Don't look at this first. Try solving it on your own, see if you can do it. Work through it, take some time, see if you can figure out this question. So the grouse grind, beautiful mountain trail, is 853 meters tall. Now the efficiency of muscle is approximately 0.25 or 25%, meaning that whenever you are using your muscles, 25% of the energy is going into making your muscles contract, doing work, lifting you up, making you run, etc. And the rest of it is not useful energy. Now the record time was 25 minutes and 1 second. This was done by a 65 kilogram man. Now if you want to think that every can of Coca-Cola has approximately 139 calories, where 1 calorie is equal to 4,184 joules, so lots of information there. How many cans of Coke would the man have to drink in order to get the energy that he needs to climb the grind? So that is the big question there. And then for part 2, what is the power output of the record holder? And part 3, how much energy would be generated as heat? So those are 3 problems there. If you're stuck, try the hints on the bottom. Please do give this a try, although it is a bonus question. It is tricky. Please give it an effort there. It'll be good for you. And lastly, we have the questions that are on the bottom. There are a total of 15 questions with the answers all the way at the bottom there. Try at least half of them. Now, we've already had our test last week, or this week, if you're looking at this on Friday. You've had your test. You don't really, you're not going to be tested on this specific topic. However, I still do want you to fill in the learning log for this week. That's the activity for the week. So once your learning log is done, submit that to me, and that will be your work for the week. So I hope you found this enjoyable and educational, and we'll see you again next week.